We're going to record some non-examples here, and one of the examples is going to be kind of silly, and the next example is going to illustrate something that will give us some intuition a little bit later. So our first non-example is 2z, or the collection of all even integers, is not a ring. So it's not a subring of C, it's not even a ring. And why is that? Well, 1 is not in 2z, so it fails the subring test. It is, however, the difference of two even integers is still even, so it's closed under subtraction, and the product of two even integers is even, so it's also closed under multiplication. Okay, but it's not a subring. Okay, I mean, very clear here, it's not a subring. The next example is going to fail for a different reason. So what we're going to do is we're going to look at the set S, and this set S is going to be the collection of all a plus b cube root 2, where this is the real cube root of 2, and a and b are rational. So this is not a subring, and in particular, therefore not a subfield. It's not a ring to begin with. So let's see that real quick. So 1 plus 0i is the same as 1 plus no cube root 2's. They're both 1. So 1 actually is in S. So it has 1. If we take two elements of S and we look at their difference, let me say these are in S. Then the difference between these guys is just, again, subtract like terms. So we have a1 minus a2 plus b1 minus b2 cube root 2. And that's certainly an S, because the difference of rational numbers remains rationals, so that's fine. So it's closed under subtraction. It's also actually closed under addition and additive inverses, which follows from it having 1 and then this property. And now we're going to see an issue here. So if we were to take a1, if we were to check closed under multiplication, so we were to take our a1 plus b1 cube root 2 and a2 plus b2 cube root 2, and we were to multiply them, what would we get? Well, by foiling, we would get a1 a2 plus a1 b2 plus a2 b1 cube root 2 plus b1 b2 cube root 4, which is cube root 2 squared. And that's a terrible b, sorry. And cube root 4 is not in S. So this fails in general to be closed under multiplication. In particular, cube root 2 times cube root 2 is not in S, very explicitly. But it's one thing to say that, right? It's like, oh, well, the cube root of 4 clearly doesn't look like that. It's a whole different thing to prove it, that the cube root of 4 is not expressible in that way. And we will get into how to do stuff like that a little bit later. But roughly what you do, so, moral homework, can show that if you were to cube something and get 4, this should have no solutions. That is, it's impossible to find a representative for the cube root of 4 using just a rational plus a rational times the cube root of 2. All right, and when we get to things a little bit later, this will, in particular, we're going to need, well, in my mind, the version that I have in my head requires the use of Gauss's lemma. But we'll get to problems like this a little bit later. For now, we're going to take it on faith that you need you can't build the cube root of 4 using just irrationals and the cube root of 2 and addition. So in particular, what we see is this is not a subring, and so it cannot possibly even be a subfield. However, if we were to fix this and we were to say, hey, I noticed that I need the cube root of 4, so let's go ahead and add that in. And if we add it in, we also need to add sort of any rational times it, because rational times it are going to naturally appear. This is something that we're going to call Q adjoin the cube root of 4, or cube root of 2 rather. And this is a subring of C, which I won't prove. We did enough proofs. And it's also a subfield of C. This is something that you're going to investigate in your homework.